I didn't say where she's from, I don't think, but you'd have to guess Florida. Yeah. Okay, so yeah, we got 3 more classes here. And we're just talking about some modifications to the ideal Rankine cycle to make it more realistic. Things that are done like in practice or whatever. This Friday at the end of class, we are going to have the last lecture quiz. So in this class, that's 5. So that's at the end of class Friday. And then we talked about the final schedule. I think the way it's scheduled is statics is, so both of these are scheduled for the last day of finals week. So that's Friday the 20th. Statics is at 8 a.m., I think, and this is at 11 a.m. For the people in both of those classes, it's just you two right now, I can definitely be flexible. It doesn't seem great to take back-to-back tests like that. Oh, the final, we're scheduled for 3 hours, but you can plan on it only taking 2 hours or less. I'm going to write it to try to make it about an hour and a half for most people. A touch longer than the usual one, but kind of in the same ballpark, But I also have finals in other classes on Wednesday and Thursday. So if either of those work for you better, I mean, that's super easy for me if you just want to take the test with another class. So just think about it and let me know. I can be sort of flexible with finals. Okay. Anybody have any homework questions or anything? Okay. So the last 3 topics in the Rankine cycle are superheat, reheat, and irreversibilities. Irreversibilities. So anyone remember what are the 2 things that make a process isentropic? This is kind of important.
Q dot equal to 0?
Yeah, so no heat transfer into or out of the system. And then the other thing is it has to be internally reversible. So this is saying those 2 processes that we think of as having no irreversibilities, how do we introduce those to make it more realistic? That's what the last one is. Okay, so superheat. So if you draw the vapor dome, we're used to state 1 being here for the ideal Rankine cycle. So we're used to it being a saturated vapor. But if you keep pumping up the temperature past that point, remember this, we're treating the boiler, or we're going to call it a steam generator now, we're treating that as isobaric. And so if you keep increasing the temperature at that same pressure, you go from a saturated vapor and turn it into a superheated vapor. And so our state 1 is actually here now. Everything else looks the same. We're still going to assume that this is isentropic. Our state 2 is down here. Our state 3. And between states 2 and 3 is a an isobaric condenser. And then from 3 to 4 is like this. And this is an isentropic pump. And then 4 to 1 is this whole thing. And that's an isobaric. Once we get past the saturation, we call this a steam generator because the mechanics of it are a little different to get past saturated vapor. Okay, so what's the purpose of doing this? Why would you do this? We talked about it in passing a long time ago.
Because you can get a lot of energy without having to change the temperature.
That's actually that's what you get during this, like inside the vapor dome. That temperature, because the vertical is the temperature, and so but what you get, remember that when we talked about the ideal efficiency of the Rankine cycle, we saw that the higher the pressure and the higher the temperature you have going into the turbine, coming out of the steam generator, the more efficiency you get. And so that's what's happening here. You're just getting more efficiency as you go to a higher pressure and temperature. So the benefit is that efficiency increases as temperature and pressure at the steam generator increase.
Temperature and pressure?
Yeah.
So
either one or the other, or both.
Sure. So like higher enthalpy. Right or no?
Higher enthalpy. So yes, I guess if you think of that as an ideal gas, that is what would happen there. Yeah. Okay, and so how does the calculation change? Nothing changes in the calculation really.
Because it's exchanging enthalpy for fluid speed? Is
that? Yeah, I guess you're really in the turbine. What you're really doing is exchanging. Well, yeah, you're using that enthalpy and turning it into work is what you're trying to do. So you're exchanging enthalpy for W dot. Nothing changes in the calculation except now that you have a superheated vapor, now you need two properties to look up any other properties. So it used to be at state 1, if we had the pressure alone or the temperature alone, usually it's pressure, then that was enough to look everything up. Now at state 1, you need two things, usually pressure and temperature. And so this is at state 1. So that's really the only thing that changes. Everything else about calculating efficiency and calculating the work generated at the turbine or the work required at the pump. None of that stuff changes at all. Okay. And we'll get into some examples, I guess, at the end. So the second one is reheat. And the way a reheat works is, so let's think of this as the isobaric steam generator. And from the steam generator, the working fluid goes to a first stage turbine. And there's very high pressure in this turbine. And from there, it goes back to the steam generator. And then to a second stage turbine with a lower pressure. And coming out of these, we have W dot for the first turbine. And I mean, you can think of this as a sum of two works, and W dot for the second turbine. And then the working fluid, now it goes back to everything that we're familiar with. It goes to the isobaric condenser. And then the pump. I didn't write this anywhere, but these are still, we're going to assume these are isentropic. And okay, the pump then goes to the steam generator. And so on a temperature entropy diagram, it looks something like this. So first, I'm going to call this state 1A. We have a superheated vapor. It goes through a turbine, but this time it doesn't get back to saturation in the first stage turbine. It stays as a superheated vapor. And I'll call this 2A. Then it goes back to the steam generator. I'll call that 1B. And then this is 2B. And then it goes through the things that we're used to. So here's state 3, 4. Okay.
And it just maximizes what you can get out of the vapor.
Yeah, so So yeah, this is really the first one that we that just takes into account practical considerations instead of like mathematical considerations. The reason that they do this is because when you have, okay, so the benefit here is that in the high pressure stage 1 turbine, because the high pressure raises the boiling point, you can get a lot of liquid in your saturated mixture. So you can get a lot of liquid in the working fluid. And that's not a mathematical problem. That's just liquid damages the turbine blades. And so instead, you get a little bit of energy out of the turbine. Don't let it get to that saturated mixture. Send it back to the heater and then to a lower pressure turbine. And you don't have that problem with so much liquid damaging the blades.
So in that first one, then is it almost like sacrificial a little bit?
Well, you still get
Or you avoid getting any liquid at all throughout this whole?
well, yeah, you can see from where it falls on the temperature entropy diagram, there's no liquid at all after the first stage turbine. The only one is in the lower pressure turbine.
So when you say in high pressure stage 1 turbine, you mean when there's just one?
Well, in this case, so what I wrote here is that the first stage turbine, they have at a really high pressure.
Mm-hmm.
The second stage is a lower pressure.
Mm-hmm.
And so
Does that always mean less work?
the pressure, the lower pressure, does that always mean less work? If you have, I suppose it, I don't know if I would say always, but if it comes in with lower enthalpy, then there's less ability to produce work, you know. So I would think typically that would be the case, yeah. Okay, so notice as far as the processes here, the process that goes from 1A to 2A, and the process that goes from 1B to 2B are isentropic turbines. And then the steam generator is the one that's a little screwy with the numbering, is, well, 4 to 1A, we're used to that being the boiler, but also 2A to 1B is also this steam generator. So these are both isobaric steam generators. And the pressure is not the same in these two. Like in each of these two processes, you have the same pressure, but you don't have the same pressure between these two. You know what I mean? It's not going back into the same steam generator. It's going back into a different section of the same thing.
So then this just like adds more columns to our.
Yeah, right. You're exactly right. It increases the ugliness kind of that efficiency calculation. So the efficiency in the reheat cycle, well, it's still W dot net over M dot divided by Q, I guess I'm still calling it Q sub B for the boiler, even though it's really called a steam generator now, over M dot.
Wait, wouldn't those M dots cancel?
Yeah, so this is just the way, but remember that coming from the control volume first law, it's just easy to get stuff in terms of works and heats per M dot. And so, yes, this is the same, since it's all steady state and everything, this is the same as saying we're calculating W divided by Q. And we can write this as W dot for turbine 1 over M dot plus W dot for turbine 2 over M dot minus W dot for the pump over M dot. So that's the network. And then for the heat, now we have the two different places where we're adding heat to the working fluid. So we're dividing by Q dot B1 over M dot plus Q dot B2 over M dot. And to calculate these, we have that W dot for turbine 1 over M dot, this all comes from that control volumes first law, is equal to specific enthalpy at state 1A minus the specific enthalpy at state 2A. Then W dot for the second turbine over M dot is equal to H1B minus H2B. Then I didn't write down the heat coming out at the condenser, but let's see. That is, so Q dot over M dot at the condenser is equal to H2B minus H3. Then we have the pump, and this is incompressible. So we have the two ways of calculating the work that's required at the pump. So W dot for the pump over M dot is equal to H4 minus H3. And we can write that as specific volume at either one of these two because it's incompressible, times the quantity pressure at 4 minus pressure at 3. So we have the two ways of doing this because it's incompressible. And then at the boiler, at the steam generator, we have two of these. So QB1 dot over M dot is H1A minus H4. And for the second time through the steam generator, Q dot B2 over M dot is H1B minus H2A. And so if you put all this stuff into this expression for the efficiency, you get that the efficiency is equal to H1A minus H2A plus the quantity H1B minus H2B minus the quantity H4 minus H3 all divided by H1A minus H4 plus H1B minus H2A. Okay, so it all gets messier to look at, but the way you go about it is the same. You're just using the information you have to find the enthalpies at all of these different states. Now you have to do it at 1, 2, 3, 4, 5, 6 states instead of 4. And then once you have all those enthalpies using the tables or whatever you have to do to get them, then you can calculate the efficiency and whatever else.
There's no clever cancellation in here.
No.
Yeah, I suppose because it's all added.
Yeah. The denominator is too complicated, I guess, to make those cancellations. But you're still going to use the fact that the two turbine processes are isentropic, and both of the two steam generator parts and the condenser are isobaric. So this is still isobaric. And this is still isentropic. Okay, and now the last thing that we'll have to do is introduce irreversibilities into these processes. So remember that the turbines and the pump are, so far treated as isentropic. That means no heat transfer, and no irreversibilities. But of course, in reality, in practice, entropy is added in both of those two processes. Let's call it generated. So entropy is generated in the turbines and the pump. Okay, so what does it look like on the temperature entropy diagram? I'm going to go back to starting with the ideal case, but all of this stuff that we just talked about with the superheating and reheating, and we can use this same idea to introduce irreversibilities into those. But so, okay, let's first think about the ideal Rankine cycle. But now we're going to acknowledge that some of this is wishful thinking. And so we're going to say that this is the, so we're going to, well, let's label what we know here. So this is our state 1. But instead of calling this one our state 2, we're going to call that the, which one am I going to call it here? I'm going to call this the state 2s. So this is like the state 2 if it was isentropic, okay? If S was constant. The real one, well, if we're generating entropy, then the real one, remember the horizontal axis is entropy, okay? And so this has to be really somewhere over here, okay? And so this is our real state 2. Then this is our state 3. Nothing changes with that. But this one we're going to call our state 4s. That's our idealized version. The real version generates entropy, so we're going to be to the right on the horizontal axis. So this is our state 4. And then we're going to go from there to here. And so what we're going to use is just a simple equation that lets us go from the 2s and the 4s to the 2 and the 4. Okay. So we're going to introduce this idea of isentropic efficiency. And we're going to do it, separately for the turbines and the pumps. And the definition of this is for the turbine, the isentropic efficiency is the work rate at the actual turbine divided by the work rate at the turbine, assuming isentropic. So this is the actual and this is if it was isentropic. And since we have expressions for these in terms of enthalpies, we can write this as H1 minus H2 over H1 minus H2S. So if we're given the isentropic efficiency, and that's just how these problems are going to be, we're going to say assume a 85% or whatever isentropic efficiency, then we can say the real enthalpy at state 2 is equal to the enthalpy at state 1 plus the isentropic efficiency times the quantity H2S minus H1. So notice all this is doing is it's just rearranging that definition of the isentropic efficiency. So this is just from rearranging the definition of the isentropic efficiency for the turbine. And it's the same thing for the pump, except in this case, we're going to flip we're going to take the reciprocal of that fraction, because so in this case, you know, the isentropic efficiency of the pump would be, now we're talking about work that's required, okay? And so the smaller of these two works is going to be the one when you have perfect efficiency, and the bigger. So to keep this thing less than 1, we're just going to take the reciprocal. So it's going to be the work required by the pump in the ideal case divided by W dot for the real case. So this is ideal. This is the smaller one. This is the actual, and this is the bigger work. And actually go up here and just make a note here that when we were talking about the turbine, this one in the numerator is the smaller one, even though in this case it's the actual, and the denominator is the larger. So perfect efficiency is when this thing is at 1. Less than perfect efficiency is when that's less than 1. Makes sense that way. And we can use these definitions and rewrite this as H4S minus H3 divided by H4 minus H3. So remember, remember not to confuse, you know, one of those has actual in the numerator, one has actual in the denominator, and it's pretty easy to make sense out of which one is which if you just think it through for a second. And we can also, because this is incompressible, we can write this as V times the quantity P4S minus P3 divided by V times the quantity P4 minus P3. Those specific volumes are the same, and so you can write this as P4 for the ideal case minus P3 divided by P4 for the actual case minus P3. This is because it's incompressible. So Uh,
So there's never vapor going through the pump.
right. So if you know the isentropic efficiency at the pump, remember with the turbine, we were able to use that to calculate H2. For this, we're able to calculate our choice of things, whether we want H4 or whether we want P4, the pressure at state 4. Okay. So we can calculate H4 as 1 over, again, we're just rearranging, and you end up with 1 over that efficiency times the quantity H4S minus H3 plus H3.
You can do that with the pressures too.
Yeah, just rearranging the other equation I gave you. So P4 is equal to 1 over the efficiency times the quantity P4S minus P3 plus computer plus P3. Okay, any questions about that? All right, I'm gonna assign a problem or two where you have to do this stuff. I haven't done any examples yet, but I'll do them on Wednesday. So, and so if you have trouble getting through the problems, just save them and we can work through any you want on Wednesday.